Hi everyone, for this video and this unit, we're talking about a concept that's pretty simple to understand, just sounds more complicated than what it is, mainly because we use this Greek word to describe this process. It's pronounced stoichiometry, and stoichiometry is a method used to calculate moles and mass of reactants and products from a balanced equation. Essentially, it's just our method of being able to calculate how much product we're going to make depending on how much reactant we put in, given the number of moles or given the mass in grams. It really comes from the ancient Greek word stoichion, which is the Greek word for elements, and anything that's an ometry is the measure and the calculation of. Okay, so it's just, again, fancy sounding language that really means something pretty simple. Okay, so what we're going to use is a balanced chemical reaction, which we should be pretty comfortable with the stuff from our previous unit where we converted moles to grams and grams to moles. Okay, so whenever we're given a balanced equation or whenever we determine a balanced equation, these numbers, the coefficients, are the key component for everything that's going to frame out our calculations. And so if we had to write a for every statement for this reaction, this decomposition of water, what we would say is because this 2 is going to be equal to 2 of that product and 1 of that product, those ratios are standard every time this reaction occurs. So we could say that for every 2 moles of H2O that react, there will be 2 moles of H2 and 1 mole of O2. So basically, these coefficients are saying that, again, remember, moles is just a number of pieces. It's not factoring in their weight. If I put in 2H2O, I'm going to get 2H2 and 1 O2. So if I put in 4,000 H2O, I can expect to get out an equal ratio number of those products based on this simplest whole number ratio. Okay? So the process that we're going to follow whenever we do a mole to mole conversion, we always have to make sure that we have a balanced equation. Okay, if we don't have any of that, we need to write the equation and then balance the reactants and the products just like we've done prior to this unit. And then we're going to use dimensional analysis, which requires the use of the coefficients to determine what we're going to now call the mole ratio to convert reactants to products. Okay, so up top it says how many moles of oxygen. We're trying to find out X mol of O2 if 5 moles of water break down or if 5 moles of water react. So we've only got one starting point. So we're going to write 5 mole, and this is where putting the label of the chemical in question is really important. We want to put H2O there because now we're going to be converting a reactant that has one formula to a product that has a different formula. Okay, so we're going to still multiply by a conversion factor, and we're still going to follow the basic principle for dimensional analysis. This label, mole H2O, goes in the bottom so that it'll cancel out. And now that we've got this balanced chemical equation and this for every statement, we know that for every 2 moles of H2O, again, taking that coefficient, putting it down there, we're going to make only 1 mole of O2. Okay, so this is now a correct conversion factor because we're taking that ratio, those coefficients from the balanced equation. So now moles and H2O are going to cancel, and by taking 5 and dividing it by 2, we'll get the value in moles of the number of O2 we'll produce. Okay, so again, this is kind of logical. If I put in 2, I get out 1. If I put in 10, I'm going to get out 5. So it goes by half. I'm going to make half the amount of O2. So if I put in 5, I should get half of 5 or 2.5. Okay, so these ratios have to stay in that same pattern regardless of the amount of reactant we put in. Okay, so we've got a couple of examples to practice this mole to mole ratio. Again, standard practice, I'd ask that you pause the video, try balancing out the reactions because you'll notice we have unbalanced chemical equations there. And then read the question, label what you're solving for, what you're given, and then try and set up the correct conversion factor. All right, so the first thing we need to do is see if we have a balanced chemical equation. And at first glance, it kind of looks like we do because we've got 1, 2, 3, 4 hydrogens over here, 1 calcium. But we've only got 1 oxygen and water, and we have 2 oxygens here because of the hydroxide being in parentheses. So in order for the oxygen atoms to be balanced, we need to place a 2 in front of H2O. And that gives us a total of 1, 2, 4 here, total of 6 hydrogens. And so we can now balance this reaction by placing a 2 in front of that H2 product. So we're trying to figure out how many moles of hydrogen gas, so X MOL is what we're solving for, if we put in 2.5 moles of calcium hydride as our reactant. So again, we've only got one starting point, so we're going to write 2.5 MOL and then the formula of our reactant, CaH2. And then as we set up our conversion factor, that label is going to go in the denominator. And then from this balanced chemical equation, for every 1 CaH2 that reacts, we're going to make 2 H2. So we can say for every 1 mole of calcium hydride, we'll produce 2 moles of H2. This allows moles CaH2 to cancel out. And if this again is in a 1 to 2 ratio, we're going to double the amount of hydrogen that we produce given the amount of that reactant. So if I put in 2.5, I should get out twice that, 5. So the mathematical process is 2.5 times 2, which again gives us 5 moles H2 is the only label left over. Right? Under our last example, we've got 2 chlorines and 2 hydrogens and only 1 of each on the reactant side. So to balance this equation, we just need to place a 2 there. And it says lead will react with an excess of hydrochloric acid to produce lead 2 chloride and hydrogen gas. All that's basically information to tell us what are we reacting, what are we producing. So it says how many moles of hydrochloric acid, HCl, are needed to completely react with 4 moles of lead. Now, the only slight difference to this problem doesn't change up much, but the only thing that's really different about this example compared to our first two is the first two examples we started with an amount of reactant and we converted to a product, basically calculating how much we anticipate to make. This example shows us the full benefit to stoichiometry because we can use it now to determine the ratio of how much other reactant we need. So if we know we have this amount to start with, we can calculate how much of the other reactant would we need to measure out so that they both are entirely used up in the reaction. Okay, so again, we've got this balanced equation. It says it's a 1 to 2 ratio. So if I have 4 moles of lead, I'm going to need 8 moles of HCl. But again, using our dimensional analysis allows us to see that ratio and how the math plays out. Okay, so if we have moles PB as our starting point, that's going to go in the denominator. And for every 1 mole PB, there's 2 moles HCl. Moles PB will cancel. And by focusing just on the labels and using the correct coefficients, it shows that we would need to multiply by 2 to get the correct amount of that reactant. Okay. Now, it really does depend on what these coefficients are. If this was a different chemical reaction and this happened to be a 5 for the coefficient, you would still put a 5 down here. Okay, so it's possible that some of these equations that have some really uh, a lot of coefficients that aren't always 1, it's possible that this ratio could be a 2/3 ratio or a 4/5 ratio. It does depend entirely on what those coefficients are from the balanced equation.